Hello, everyone, and welcome to this week's seminar by PermafrostNet. Our speaker today is Galina Jonat, and I would like to introduce her quickly. So, Galina is a PhD candidate researching permafrost modeling under the supervision of Stefan Gruber. Her work focuses on reducing uncertainties in simulations of future permafrost change to make them more useful for decision makers. In addition to her computational work, Galina has participated in field campaigns in Chief Dragi's territory, the traditional land of the Yellowknives Dene First Nation. These experiences have provided real-world context and opportunities to learn from the people who experience permafrost change firsthand. Outside of research, Galina volunteers with the Canadian Ski Patrol and enjoys hiking, running, eating waffles, and exploring Ottawa by bike. Galina, whenever you're ready.
Cool. Thanks, Gabe. And thanks everyone for being here. I'm excited to finally be giving this talk. So today I want to talk to you about the work I've been doing around improving predictions of permafrost conditions, specifically in the context of using future climate data to predict future permafrost change. So as Gabriel already mentioned in his introduction, I'm hoping to improve simulations of permafrost change such that they can be used by decision makers. And while doing that, I'm trying to take into account the local variation in ground conditions, local variations in climate, and uncertainties related to these components, as well as future climate conditions. And what that looks like, we'll see a little bit later when I introduce my research questions. We're going to start with a little background primer, and then we're going to show one example that illustrates the approach I've been taking to solve this problem or on my way to solving this problem. So first of all, I would like to explain what a permafrost model is. So a permafrost model is based on physical laws which control the thermal state of the ground and its interaction with the atmosphere. And it's useful because we can usually not see it at the Earth's surface. And so we want to investigate both past, current, and future state of permafrost. When I talk about permafrost models, I usually talk about transient permafrost models, which are, again, a physical representation of how atmospheric forcing translate to changes in the ground, but specifically how these changes happen over time rather than a snapshot at one specific point in time. So again, why permafrost models are useful, we see this beautiful map here of observations that we have. And we see that there's a lot of places where we know there is permafrost where we don't have observations. So we're able to provide permafrost information for time periods and places where direct measurements are not available. And to do that, we make use of climate models and climate model products. Just thinking about what a climate model is. So it's a big physical model that simulates the transfer of energy and materials throughout the climate system. So between the ocean and the atmosphere and the land, and also through scenarios, we also see what the impact of humans is. And I also thought that here it would be important to describe the difference between weather and climate. So weather is something that we observe on our day-to-day basis. When we have a weather forecast, we know that what the temperature is going to be tomorrow, what the precipitation is going to be tomorrow, what the winds are going to look like. But when we think about climate, in contrast to that, we think about longer term trends or longer term patterns. So for example, we can look at the June temperature of a certain place over 30 years. So that can give us some idea of what to expect in the next year. So when we talk about climate, we consider long-term periods. A climatological period is defined to be 30 years. And when we think about weather, we think about day-to-day observations and or day-to-day forecasts, which will be important when we go later into this presentation. When we talk about climate models, we also shouldn't forget about climate scenarios, which are our way of looking into the future. The reason that there are multiple climate scenarios are that we don't know what's actually going to happen, how humans are going to react to changes in the atmosphere and how our emissions are going to evolve. So there's two types of climate scenarios that have been developed kind of in tandem with each other. One is called the RCP, which are representative concentration pathways, and the other ones are called shared socioeconomic pathways. And they have a couple of scenarios where they look into the RCPs are more focused on what the atmospheric energy that is kind of a surplus that's coming into the atmosphere is going to look like, whereas the shared socioeconomic pathways are in their basis more about the human action, but they're complementary to each other and can easily be compared. And in my experiments, I'm using a climate model suite that is called CMIP6, and they are using the SSP scenarios. And finally, we have reanalyses, and reanalyses are a combination of past short-range weather forecasts with observations. So it's basically like a little climate model, but it can be run on a smaller grid, and it can be corrected by all the observations that we're able to have on the ground. And the cool thing about reanalyses, again, because in the north we don't have a ton of weather stations available, they can actually fill some of the gaps that we have, both in terms of time, but also in terms of locations where we not necessarily have observations available at a specific point. And when we think about it later, about the timescales on which we try to compare and make decisions, having reanalysis data that goes far back in time, again, allows us to consider our climate data and how well it was able to represent our past and make a guess of how well it will represent our future when we have that long-term reference, similar to permafrost models. When we run them with reanalyses that go over a long period of time, then we have a longer term data set that we compare against. And that is very useful, as we will see. So how do they all fit together? And kind of put together a little timeline here. So we have reanalyses data sets that go back to 1850. There's climate model data that goes back to 1850. Some even goes back to 1500, I think. And then we have the climate model predictions that apply sort of the scenarios, so the guesses of how the forcing is going to change given human behavior. And then in the bottom here, put permafrost observations in a dashed line, because we do have permafrost observations in some locations for longer periods, but sometimes there's gaps in them. And obviously for quite a few sites, we only have a couple of years of observations. So when we think about using climate models in side-scale permafrost simulations, we have a couple of challenges that we are grappling with, mainly being resolution, topography, and also site variation of the ground, which is why we can't just use the climate model directly and kind of say, okay, and this is what we expect the permafrost to look like when we have this air temperature. So when we think about the resolution of climate model data, I put one of the Canadian Earth System model, which is one of the climate models that I'm using on top of this area here, which is in the Lac de Gras region. And so we basically have the same temperature data for this entire cell. And as you might expect, actually being closer to a water body might change how the temperature changes. And also if we introduce topography, so if we're like in a mountain or it's higher or lower, we got to think about the fact that, again, for one of these cells, this temperature value is all the same, which might not be the best way to guess our permafrost simulations. So the way we're addressing it is by using a method that is called bias correction. So when I talk about bias, I talk about the mismatch between the model data and the reference data or observation data. And again, as we know that they're not synchronized, we're thinking about the mismatch between the distributions of each of those. So kind of thinking about the maximum and minimum temperatures or the annual mean temperature, or the same with precipitation. And what bias correction does is that it aligns the distribution of the model data with reference observation data, so correcting that mismatch to some extent. All the methods that I use in my experiments are multivariate bias correction algorithms, which not only take into account the mismatch between observed and model temperature, but also look at the relationships between those variables. So, for example, between air temperature and precipitation, or incoming radiation and temperature, and all these kind of things. And the reason this is cool is because as the climate changes, we might not see the same distributions of each of these variables. And so the dependencies, if we expect them to stay the same, they adjust with the future climate. And then again, thinking about the ground, we have the variation of surface and ground conditions, which can even vary a lot over a couple 100 meters. So when we think about how to address all of these things, a student in the lab, Hannah McDonald, I think she already gave a seminar, has put together an approach which I've summarized very, very briefly here. So what she did is she used a tool to prepare the reanalysis data, and because it's not a point scale, she used some corrections for topography and for the location of the points that she was interested in. And then she made some assumptions about the ground parameters, plugged that into a permafrost model, and examined the output data. And that approach allowed her to select the best fitted reanalysis and ground parameter pairing that she could test with short-term observations. Now, this is cool because she used the reanalysis data, which we said is running over longer periods of time. So that means that also the permafrost simulation output data that she has tested and she has sort of a quality measure on is a longer period of time than just the raw observations. So we can use that to test in our climate model. So I took Hannah's work and the work of a lot of other people who contributed to this and plugged this into my own approach. I used the reference data that she had selected or ranked, sort of the best fitted reference data, to prepare my climate data, so to bias correct the data that I can use to then drive my permafrost models. The parameters, again, if I knew how the site was configured, I can use that directly or a couple of those configurations. And then at the end, I have a way to evaluate my permafrost simulation against a long-term reference data set that has been tested and which uncertainties have been quantified. So with all this kind of method given and background, I was looking into how bias correction would improve the representation of climate forcing at specific locations and what the implications of these corrections are for simulations of future permafrost change. To give one last point of complexity, I guess, to my evaluation, I thought about showing you how we are able to compare observations and models with each other and where that kind of breaks down. So when we have observations at a site, we usually have meteorological station data or reanalysis data, and we have permafrost observation data, ideally. On the modeling side, we have reanalysis data, which we use to run a permafrost model and get permafrost simulation data out with that reanalysis data, which we learned is time synchronous. So because this is time synchronous, we're able to compare and correct them directly, both in the kind of atmospheric realm, but also on the permafrost level. And as I mentioned before, we can extend local observation time series. On the other side, we have climate model data, which we use to drive a permafrost model and get our permafrost simulation data out. This is expressing long-term climatologies. So again, it's not kind of a day-by-day prediction. It's more so a long-term trend, long-term averages that we're looking into here. So that means we cannot compare them time synchronously and instead need to look at distributions of these, which we're going to see how we do that in practice later on. So let's move over to our example experiment. For this, I was initially thinking to show you 2 sites, but actually I have so much material for one site that I thought it would be better to focus just on one. But this is a site that is located north of Inuvik, just next to the Inuvik-Tuktoyaktuk Highway. And when we zoom in, we see that we have some polygonal terrain, pretty low vegetation, some puddles going on. So first of all, we start by looking at the climate data. And this is a lot of information. So here I show you kind of what the air temperature looks like at this location. And the black line that you see here is our reference data. And to make a bit more sense of the spaghetti plot, I summarize these in multi-model means. So if we look at the air temperature data, and we have observation data until like 2019, as it looks like, and in the blue color, we see the original climate model mean and standard deviation. And in the orange color, we see the bias corrected one. So again, where we try to better align the climate data with the observation distribution data set. And 2 things I would like to point out. So one is that because we're correcting distributions and not day-by-day basis, it means that we keep the trend. So the blue and the orange line are running more or less in parallel, but we see that the warm bias that we had in the original climate models is partially removed through the bias corrected climate model. So that is pretty good. The other thing that we see is that we can reduce uncertainty, or we can reduce model spread by using bias correction, at least for this air temperature variable that we're looking at here. So if we look at the model spread for 2050, for example, so this would be almost like a 4-degree stretch here. And I think from here to here is more like a 2.5-degree stretch. So in terms of how are we better to express air temperature at our location and also reduce the uncertainty using the exact same models that basically came from the blue as input is quite significant. The other thing I would like to point out is that even though we preserved the trend, this correction also showed that by the end of the century, we have a temperature difference in the model means by 1 degree Celsius, which is quite a lot in terms of air temperature that we expect to change. And the other thing that we can see is that the model spread for the original model gets quite large, whereas for the biased climate data, it gets larger, but it still stays smaller than the original one. So again, because we can't compare this data directly one by one, the other way to select the best data is actually by looking at summary statistics. So here I just wanted to illustrate what I mean by correcting the distributions of each of these variables, but also the intervariable dependencies. So we have the original climate model on the right-hand side, and you see that the original distribution in the historical period is quite different than the black line, which is our reference data. And there's a lot of days that we don't have precipitation. So this is why this plot looks a little bit confusing. But what we can see is that there are a few outliers here that we're not able to cover, that in the bias corrected data are a little better covered. And when we look at air temperature again, we see that this distribution of the orange plot is better fitted to the reference data set, which is the black line. So we're pretty happy with that. Then we're looking into how does that actually translate into the ground. So again, we have our spaghetti plot of the ground surface temperature with the black line being the reference data. And again, it's pretty hard to actually derive anything from all of these. So we're looking at multi-model means. And what's interesting here is when we think about the simulated ground surface temperature with the bias corrected climate model data, it actually looks farther away than the simulated ground temperatures from just the original climate model data. And we're currently looking into why that is, or how that is happening. But the other interesting thing is that the reduction that we saw in the model spread for the bias-corrected data actually doesn't translate in a reduction of the model spread when we think about ground surface temperature versus the air temperature. So that we kind of see the same trend at 1 meter depth. It's a little bit better, but that is also due to the original climate data-driven simulations more or less being aligned with the bias-corrected data-driven simulations. And that will be a level to look into later, is how much actually certain things impact our simulations. But again, what we can see is that we're still not able to, we're kind of overestimating almost the entire way what the ground temperatures have looked like in the past. And so I looked more into how can we select a subset in the time series. So this is a lot of colors, but I'm going to walk you through it. So we have the blue as before the original climate model data, and you see the model spread here. Then we have the bias-corrected data, all of it, in the orange color as we had before. So this is kind of the same plot as what concerns those. And then I added two more selection criteria. So first of all, I selected the best fitted climate data overall that includes all of our climate variables and measured how far they are from the observation data set. And that actually gives a huge warm bias, but in the historical data, it's actually a little better fitted. As you can see here, the little green line is a little bit closer to our observation data. And when we select only in terms of, because we think that temperature and precipitation could be the dominant drivers of ground temperatures compared to some other variables that we're using, this would be the purple line. But it seems like the uncertainties are lower and the overall result is lower when we think of the end of the century. But again, we have quite a bit of model spread. So selecting those time series and how we select, if we select on the climate model level or on a permafrost level, is something that I need to investigate a little bit further and kind of see how that impacts my time series and how that impacts the predictions. So one of the ways that we can look at it again is in terms of distributions. One of the ways that we can compare distributions is by using box plots. So they kind of show the model mean and the stretch here, and then they show the most dense area here. And then this is the standard deviation that we see. So if we look at the reanalysis distribution, we see that this is pretty cold compared to the mean is pretty cold compared to the other ones. And also like the standard deviation in terms of we have quite a few values in the cold area as well. And so compared to the original climate model, that seems to have a bit of a warm bias here. We're just a little bit too warm. Interestingly enough, when we take all the bias-corrected climate models, we get even warmer. And again, I will need to look into why that happens. But when I select, and that's kind of a self-fulfilled prophecy, the climate models that best fit the reanalysis data based on how that best fit the ground temperature data, we get a distribution that is closer to this original one. So this is just something to think about and something that I will need to look further into why that is and where we actually need to make our selections. So finally, for our key takeaways, I would argue that the performance of the climate model forcing data needs to be evaluated at the permafrost level, because from what we saw when we look at the climate driving data, it doesn't tell the whole story. And depending on what climate variables we're comparing or using to choose the permafrost data, we can't be super sure about how that will translate into changes in the ground. And that will also be for permafrost metrics beyond ground surface temperature or ground temperature at 1 meter. Would be interesting to look at thaw depth as well. And so one of the things I want to look at in the coming weeks, or that I'm actually looking at right now, is how this performance varies when we have different ground conditions and topography. And when we look at other permafrost metrics, is kind of the best fitted climate data still performing in the way that we see with the ground temperatures, or does it look different? And the other thing that we saw in the plot is I would like to see which factors are contributing most to uncertainties, depending on which timelines we're talking about or which permafrost terrains we're talking about. Yeah, that's all that I had for today. I'm happy to take questions.
Thank you very much, Galina. It seems we have one question in the chat already.
Yeah, thank you, Gabriel. I was just wondering, maybe then later I get the answer, but it's mainly regarding this downscaled data of SEMIP6 because it's already available using the MBCN. We have this downscaled and bias correction SEMIP6 data. But here, Galina is only using MBCN for bias correction. But I think that's mainly because she's using also the ground temperature, which is not available with the downscaled data. We only have temperature and precipitation. Yeah, so just need some clarification. And yeah, thank you so much for this presentation, Galina. It's really great.
Yeah, thank you. And thank you for that question. So one thing that I didn't show is that to run my permafrost model, I actually use more climate variables than just temperature and precipitation. I just feel like I showed them because they're the most accessible, in my opinion, for people to understand how this whole principle works. But I'm also using wind speed and wind direction. I'm using pressure, shortwave radiation, and longwave radiation. And so for me, it was interesting, or one of my questions is, which of the bias correction methods perform best? So that's why I performed all of them with the same reanalysis reference data in order to make them more comparable. And then because we run our permafrost model with the same reanalysis data, that kind of correction chain allows me to evaluate both the climate and the permafrost data on the same premises. But I will definitely look into the data that you were talking about. I was actually not aware of that. So thank you for that.
Great. Igor, you have a question?
Yes, thank you very much, Galina. Very interesting presentation. For engineers, we are very concerned about the design of permafrost foundations, and that actually a very interesting topic, how to calculate the future temperatures, air temperatures, surface temperatures, and ground temperatures, and how to actually compare with the registered temperatures on the surface, right? Which model would be the closest to the registered temperature. So you said that you used only one model of, I'm talking about the air temperature. So if you create a model, climate model, so can you consider this as a regional parameter and then registered temperature, let's say, on the construction site, consider as a local temperature, and probably there is some deviation from the regional parameter, right? So how can I, let's say, calculate these deviations, or how can I train my regional model to the local registered variations of the temperature, let's say air temperature?
Yeah, thank you for your question. I think if I understand it correctly, so the first point I should clarify is that I use a number of the CMIP6 models for this location that I bias correct. So that's why we have this big model spread in air temperature that I showed before.
And which model would be closest? Did you compare all these models with the correlation with your local registered data, right?
Yeah, so what I did, because CMIP6 has a big range of models, there was a natural down selection at first because not all of them had all the variables available that I needed to run my permafrost model. And then what I did was because again, we don't really know what's going to happen in the future. So we need to still think about the model spread, even though not all of them might be the best fitted models. So I looked at, first of all, I checked how each of these models, because they're not necessarily independent. So the way that the climate models are designed, they may use components from one or another modeling office, I would say, for specific parameters. So I looked, first of all, that I would get kind of a range that captured I did some sort of clustering that I would get the range of intervariable dependencies, but also of the distributions. And the only thing that I kicked out at that point was things that seemed completely unrealistic in terms of where my reference data lay for these types of points. But then I think the best thing to do is using model ensembles, and then using ensemble means and standard deviation as your best guess and also as a measure of uncertainty.
Is there any way to tune your model to be closer to your registered data? Let's say changing different parameters or using some factor analysis or other things?
Yeah,
Is
so
there
that's
a
what
way
I'm
to
doing
make
with
it-
the bias correction.
I see, okay. Yeah, thank you very much. And the second question, how did you calculate, let's say, the ground temperature? As a usual way from January 1st to January 1st, how do you calculated your mean annual ground temperature for that?
Yeah, so this is just a yearly mean summary. So I ran a simulation over the entire period. So I spun up my model and I ran the simulations, and then, yeah, I did January to December. I just did a yearly.
On each depth, you do the same from
Yes.
January to December, each depth, right?
Yeah.
I see. Okay. Thank you.
It seems that Chris Spence, have you looked at precipitation? Chris, would it be possible for you to clarify this question?
Yeah, just like you've done with temperature, have you tried to downscale the precipitation?
Yes. Yeah, I didn't make that
Yeah.
clear. I thought temperature I picked temperature as an example to illustrate, but I actually downscaled all of the variables that I used to run my permafrost model. So that includes precipitation.
Yeah. How did that go? The precipitation.
Well, this area is in general pretty dry. So I mostly looked at how the dependency between temperature and precipitation was improved versus just looking at the precipitation by itself, because that is really hard to determine.
Yeah. Okay. Thanks.
Yeah, thank you. It's just regarding the permafrost model, Galina, just if you can elaborate a bit on it. So it's a physical model, I guess, so calibrated, where is calibrated, and yeah, some details about the model, please.
Yeah, so I used the geotop permafrost model, and the way it's calibrated is by, so we just run a bunch of different simulations, and for sites that we have observations for, Hannah has developed a nice ranking framework to find the best fitted ground parameters to drive the geotop permafrost model, which she compares to actual observations, if that answers your question.
Yeah, thank you.
All right. I'd like to thank everyone for attending this week's PermafrostNet seminar, and please stay tuned for the next one. Have a good day, everyone.